Hi students, today we will be seeing the concept of synchronization and tracking. So previous class we saw the different multiple access FDMA, TDMA and CDMA by using the PN sequence code. We make sure that proper correlation between the correlated sequence between the transmitter and the receiver. So here you will go the last topic of this unit, continuation of the FHSS frequency hopping spread down. Under that you have this synchronization and tracking. So FSHS, the synchronization in an urgent communication system, how it is being used. So the basic principle lies is similar to the DSSS. However, some difference is there in the diagram. So there are three techniques of acquisition of FHSS signal. So here, if a FHSS network fails to synchronize, it cannot communicate. For example, uh, if it cannot able to synchronize its PN sequence with the receiver or transmitter, okay, it cannot communicate. So in a channel, it shares the PN sequence. The receiver and the transmitter knows the PN sequence code in such a way that the message, printed and message signal is being received. So here, if the synchronization is not performed properly in a network, so there may be a chance of data to be lost. So a jammer can try to attack for the synchronization process, but it must know when synchronization is occurring to be successful. So a jammer in a channel can able to get your data by knowing the synchronization process, okay, or attacking the synchronization. So it should be avoided. So next one, however, such attacks can very be productive. So these attacks are very much prone to the communication channel. So the process of synchronization is more important in the mostly in the FHSS as well as DSSS principles. So the environment consists of push to talk network. Let us take a push to talk network for where there may be extended period of no communications. So there is an application for push to talk in where they use this in a military application. Okay, so they have a button, they push the button and they try to talk and take it away. So in that intermediate process, okay, the synchronization has processing is being done. So it makes sure the enemy or anyone doesn't try to jam the signal. Okay, so if there is an extension, the period get extended a long time. Okay, so if there is a delay or jitter, so there comes the problem of synchronization. So one packet, let us take a packets of signal. One packet is there and having a after that a very long time. That's another packet. There is a very much delay. Okay, here. So it makes sure the synchronization of this packet may not be achieved. It may be the packets may be dropped off. So there is a specific application like push to talk networks. They rigorously use this synchronization, a very much important protocol. So in this time, the clock in the transmitter and receiver may have drifted apart, okay, and that's causing the PN sequence to be out of sync. So the clock signals between the transmitter and signal receiver maybe drifted apart, they are delayed apart, such a way that it affects the PN sequence code. We already know that there is a PN sequence generator. It generates a random sequence of bits like 0 1 0 0 1. Okay, it generates up to like n number of bits. So rapid random sequence bits. So these bits will be known by the receiver too. So if there is no proper synchronization or out of sync, okay, so there is a drifting apart from there is a drifting of clock sequence between the time at a transmitter and receiver. where you cannot able to retrieve the sequence. So for each before each transmission, the transmitter receiver have to be synchronized. So the only process we have to do is before transmitting any data, the transmitter and the receiver section has to be synchronized first. Okay, so that's the topic, synchronization. So if you use a frequency hopping between different frequency F1, F1 hopped between different frequency, all the frequency, preceding frequency has to be linked. Okay, so such a way that there is no drop in the any packets. So here, this is one diagram where you can see. So from this block diagram, it's a continuation of this uh, synchronization. So here FFS or MFS demodulator has been used. So in this diagram, both the DS and FS, so the spectrum receiver is being synchronized, replica of the splitting codes. So from this figure, so we can able to make an acquisition. Okay, there is a word called acquisition. That's the first step we have to do. So it consisting of bringing the two splitting signal into close alignment with one another. That's definition of acquisition. So acquisition means like bringing the two splitting signal, any two splitted signals into alignment with one another. So because of the timing difference, there may be a chance of misalignment. So that has to be rectified, right? So there is a process called acquisition that has to be done in the synchronization process, such a way that the sequence are being uh, to any two or three sequence, any two sequence or three or more is been course aligned, okay, with one another. So there is an alignment has to be done such a way that it doesn't go away from the sequence. So once the received spectrum signal acquired it, the second step is called tracking. Okay, on the receiver side, it does the tracking. It takes over and continuously maintain the best possible waveform, get finely aligned with respect to some feedback loop. So there is on the receiver there is a feedback loop, and there is a tracking process going on, continuously maintaining and giving a best possible waveform. Okay, that's what is being given. So in this F demodulator, you can see like there is a receiving popping signal. So it is being received by some antenna. Okay, so uh, this portion is an antenna receiver. So it receives some signals, or packets of signals. If there's a mixer, that's mixed with the frequency hopper. Okay, and they've been filtered out, getting taking away the unwanted signals, and it's given to envelope detector. So it's given to M envelope detector. There is a clipping circuit, okay, and a set of accumulators. Summator has been added. All together, it's given to decision device. Okay, so it tends to track the signal. So there is a process of tracking being going on the receiver side. Okay, with a different splitting of signal, envelope detector by up to m minus 1. M is the number of sequence. So it sees the any clippers. This sequence has been clipped off, okay, and it's been given to an accumulator to add all the sequence. So here at the decision device, it decides the tracking sequence with the maintain continuously the waveform with a fine alignment. So it aligns properly with respect to this sequence code. So this decision device it choose the maximum number of sequence, okay, which is acquired from the signal, and this makes sure the process of alignment been is being done properly. So problem here is like there is a chance of clock being unsynchronized. Okay, between the transmitter and receiver. So it makes it directly affects the PN sequence code. So there should be some proper retrieval system on the receiver. Such a way, all the blocks has been properly aligned, okay, and gives you a proper waveform. Next one, the acquisition problem is one of this. That is like it surges throughout the region of time and frequency. Okay, in order to synchronize the receiver spectrum signal. Okay, so it synchronizes the receiver's received spectrum signal. Okay, with respect to throughout the time and frequency. Okay, it doesn't hold on with some time period. It synchronizes throughout the region of time and frequency, and in par with the local generated specific signal. There is a local oscillator with the receiver, right? So in par with that, it tries to sync with the received spectrum. So uh, this can be classified. This can be classified as two things. Okay. So acquisition can be classified as a concurrent and non-concurrent. Okay, it can be classified as two types as concurrent and non-concurrent kind of dispute. So we have used this FHSS DSSS is a non-concurrent based of where it doesn't have a timing and a frequency. Uh, what do you say, like acquisition and tracking doesn't have. But in a concurrent scheme, you should that with timing and with respect to the acquisition and tracking with respect to time and frequency. Okay, so so here the desplitting process take place at the receiver. It take place before the carrier synchronization. When the carrier gets synchronized, okay, at the final, the desplitting is being done. So therefore, the carrier phase is unknown at this point. Okay, carrier phase is unknown at this point, and most of the acquisition is a non-concurrent direction. So we have some limitation of uncertainty in time and frequency. Also, some points we have to take while doing the de-spreading process. So at the receiver, the code is going to be spreaded, okay, with respect to different frequency. If you take FHSS, it's spreaded according to different frequency hopping regions. So under that, if you have a non-concurrent direction, okay, some limitations are there that has to be considered. So uncertainty in the distance between transmitter and receiver, okay, translates into uncertainty in the amount of propagation delay. So there is a the transmitter and receiver between the distance, okay, should be as noted down because it directly relates to the delay, propagation delay. Okay, just there is a problem called near and far. Okay, when you have a mobile phone at nearer region and when you have a mobile phone at a farther region respect to the base station, so it has to allocate the power properly. Okay, so such a way that there may be a chance of propagation delay gamma. So the nearer mobile phone can get the more number of strength signal strength rather than the mobile phone which is away from the base station. So this uncertainty is more important with respect to the distance. Okay, so why we focus on this, like the the clock uh, the clock signal is more important for different users. So if the clock signal is not been is been altered, okay, unsynchronized, there is as I already said that the PN sequence will be affected. Okay, so there is a they need used to the process of jamming, okay, or data being tampered away. So second one is the relative clock instabilities between the transmitter and receiver result in phase difference. So clock instabilities, that's what I said. Uh, there is a stability criteria for the synchronization of clock with the transparent receiver. So it directly affects with the phase of the signal between the transparent receiving splitting signals. If the phase has been altered, okay, so ultimately the whole bit can be halted. A sequence of bit can be halted. So phase has to be taken into consideration because some systems they have phase shifters, okay, to bring back the correct phase. So the transmitter and receiver should be in par with the clock synchronized, and the phase ideas should be mutually being shared. So this will tends to grow a function of elapsed time between synchronization. So because of this phase difference, there will be a big elapsed time between the synchronization process. It doesn't do the synchronization quickly, so it takes some more time. So the bandwidth is not perfectly utilized. There is a loss of signal also. So third one, uncertainty of the receiver related velocity and respect to transmitter translate into uncertainty the value of Doppler frequency offset. So there is on the receiver side, the relative velocity is more uncertain with respect to the transmitter. So there is a Doppler frequency offset value, DC offset. Some value has been given for the incoming signal. So the receiver doesn't have a proper correlation with this incoming Doppler signal. So there tends to change the offset value. Okay, so in that case, you have some uncertainty between the transmitter and receiver. Second one, relative oscillators instabilities between the transmitter and receiver. Research frequency offset. So there is a two signals being transmitted same channel. So the frequency can be offsetted or turned over when you have an instability in the oscillator. So we have used local oscillators, right? We have used local oscillators. We have used phase oscillators. So there are some oscillators we try to use for the circuit. If there is some instability with this oscillator, it will directly affect the frequency. A frequency get offsetted some errors. So returning back that frequency is very much difficult. So this has to be taken care. So these things all affects the clock instability, and it may if you have a clock instability or oscillator instability or some velocity a Doppler shift offset. So this will thing will make up not doesn't have a proper synchronization between transmitter and receiver. So here, how this acquisition is done by searching. Okay, searching with respect to time and frequency. So there are like serial search and the parallel search. Okay, so there are two types. So we will see about this say searching. Okay, so here at this structure which you're seeing, okay, it's a parallel search acquisition where you have a received signal. Port signal has been and it's been a locally generated code is there. Okay, so there is some oscillator and G of t, and G of t minus G, so it generates up to a sequence with respect to different locally generated oscillator, and then it is integrated with 0 to lambda tc and comparator. So this structure is there. It uses the parallel search acquisition. So here there may be a false alarm in the circuit. Okay, where the threshold may be further crossing in a different value. So this has to be taken care. So this parallel search makes sure the local generated code G of t is available with the delay. Okay, it is paced with the one half chip of PC by 2. Okay, so there is a local generated G of t available. So this is a delay element. Okay, there is a minus being added, right? So these are all delay. When you have in the circuit you have a minus minus 1, okay, minus j tc by 2 tc by 2. So this tc by minus j tc by 2 is a delay element with a one half chip. Okay, one chip. Okay, we are taking tc as the one chip time chip duration. So you take in half of it. Okay, that's TCP. So if the time uncertainty between the local code and the receive code is NC chip, so there's a local code being generated and the received code. Okay, you're going to compare it together. Altogether, you get some NC chip and the complete parallel search entire time, and it search for the entire time for the region and accomplish a single search time. Okay, so here this is nothing but searching. Okay, searching with respect to time. That's G of t. So why this searching is mainly used to synchronize with the transmitter and receiver. You see that any improper synchronized data is there or not. So each correlator simultaneously examines the sequence of lambda chip. So these correlators, that is lambda, that's a correlator. So this will examine all the sequence g of t with the chip duration of the chip TCP2. Examples and give the sequence lambda chips. Okay, that's a variable lambda, some value lambda chip number of chips it will give. After that, it will give two NC correlated output or compiled. So output is twice of NC. So there is a receive code, there is a delay element, there is a correlation being done with this integration, and there is a comparison. It compares all the input and it gives the output. Okay, compare the output. So the local generated codes corresponding to this correlator will give the largest output. So output will be twice of it of the received code. Okay. So this is the simplest of the search technique. It consider all possible code positions. Okay, in parallel and use the one algorithm called maximum likelihood algorithm to acquire the code. So detected output, it is nothing but is identical of the receiver signal plus noise. So the output is the detected output is nothing but the received is the total received signal, and it has an additional noise. Okay, if lambda increases, you have a lambda there, that's a chip. Okay, if lambda increases, the synchronization error probability decreases. So what is synchronization error probability is choosing the incorrect code alignment. Okay, so if the lambda increases, the incorrect code alignment, the probability of incorrect code alignment will be decreased. So the code has to be aligned properly at this output, but the output is having more number of code. Okay, and it makes sure that all codes are positioned properly parallelly. They use the algorithm called maximum likelihood algorithm to acquire these codes. Okay, so the proper synchronization can be done with all the codes. So the lambda is chosen as a bit compromise between the minimizing the probability of synchronization error and minimizing the time to acquire. Okay, so the lambda should be as a minimum value, such a way that the incorrect alignment is not increased but it's decreased. Okay, we call that as a synchronization error. So the timing should be as low as possible. We cannot increase the more number of time to synchronize. Okay, so if you increase the time, it may the data may be lost away. So we must make sure that timing is minimized. Synchronization error is low as possible. Lambda should be minimum. Okay. So figure 12.18, that is the second figure. It defines the frequency hopping acquisition scheme. So here we saw the direct sequence with respect DSS with respect to parallel search acquisition. Similarly, we can able to see in the system like frequency hopping. How can we synchronize in the frequency hopping technique, which is a diagram. So here we use a delay input signal is there. Okay, there is a input signal then coming from the transmitter. Okay, and there is a delay element with respect to frequency. There's a band pass filter, square law detector. There's a delay element. Okay, n minus one halves, n minus two halves. There's a summator and there's a output. So here, how the synchronization has been done? Let us see. Let us see n consecutive. Let us have a n consecutive frequencies from the hop sequence. So there is a frequency hopping, right? There are n number of frequencies being hopped, where every frequency should be properly synchronized. So here the n non-coherent filters are used. Okay, so we use the bandpass filter and the square law envelope detector. So this envelope detector is followed by a square law device. Okay, so if the hopped sequence, for example, F1, F2 up to Fn delays are installed in the matched filter, the correct frequency hopping appears at the system at the larger output. So what happens here is like the on the block diagram, we have n number of F1, F2, Fn of hopped frequency sequence, and is given to a bandpass filter. Okay, so this bandpass filter is a non-coherent matched filter. It follows a square law detector. Okay, so this has been make sure that proper frequencies been band limited, detected, and delayed. Okay, so it finds out the proper code sequence. Okay, it detects, and if there is any bit longer time difference, it delays the hop. So if the two different hopping is having a very large time constraint, like one hop you have here, one hop you have a certain distance away from it. So this timing error is there. Okay, if you hop it more greater distance. So one hop you has, consequently next hop will be there. Okay, consequently another hop should be there. So this has to be maintained by the delay n minus one hops, and at last it is being summated together. All should be added together and properly synchronized. So that is the main thing which will be going on the FHSS. So acquisition is acquired rapidly by all possible code offsets. Okay, by it has been done for the all the possible input codes which is coming. Okay, so the presence of this bandpass filter indicates the local oscillators, that is the F1, F2, Fn, chooses to have an offset of some intermediate frequency. So this offset frequency will make sure the local frequency will make sure to have an offset value. It also have a specific offset, DC offset value, that is being synchronized with all the frequencies. So if one or two frequency is not been properly offset, there will be a chance of uh, code being uh, acquired at a different sequence. Okay, the code cannot be acquired properly. So all this F1, F2, Fn should be synchronized with the offset value. So the same system can be implemented without offset also at the baseband signals. Then you use the filter, for example, low pass filter. Okay, so if you use a different filters, the mixer are typically in a complex and yield a in phase and quadrature term. So either you can use DPF or LPF. So you should make sure that the offset, either you are going to use the offset value or not going to use the offset value. So here the one formula is given: T acquisition, time acquisition, maximum bracket maximum is called lambda EC. Okay, so that one formula is given, that defines the uh, maximum time required for the full parallel search. Since we are dealing with the parallel search, so how much time is required for the full parallel search of the codes? Okay, it depends on the chip lambda and the TC. Okay, that is chip duration. So it's a multiplication of lambda, and this lambda should be as minimum as possible. as I already said that, and you have a chip duration. Chip duration should be as somewhat minimum as possible. Okay, so you cannot increase further longer chip duration. So it will also affects the synchronization process. So the mean acquisition time of the parallels can be approximated uh, by integrating the lambda chip. So okay, you can integrate. We have seen the previous block. You can integrate the with respect to the lambda chip and give it to the decision process. Okay. So next formula is given T acquisition. Okay, that's the average acquisition time. So previously with the maximum time acquisition time we have taken, but for the average we are going to average all the acquisition time. So it is a addition of all the chip, okay, and the time chip duration, but you have a PD there. That's the probability of detection. PD is nothing but probability of detection. So this probability of detection is mainly focused on the uh, detector side. Okay, there is a chip detector at the last. So there you have this probability of detection built in. So it's nothing but if an incorrect output is chosen, and additionally lambda chips are again examined to make determination of the correct output. So the average, so incorrect data, if it is you have chosen, if it is chosen the decision level, so it must make sure the further the lambda chips are being added and it is being averaged out to find out the proper position. So T acquisition is lambda TC by PD. So probability of detection. So here it requires a number of correlators or matched filters. So it gives you a full acquisition, parallel acquisition. Um, Apart from the two figures which you have seen, we have used a correlator and filters to implement the parallel. Okay. Similarly, we can also use the same concept to uh, find out a serial search. Okay. So nothing but the combination of this mixer and the correlator is quite different with respect to time. Okay, time and chip rate. So similarly, we are going to see another search called serial search. So this all comes under the acquisition. Okay, the parallel search and serial search. So here that's a formula which is being given: the total maximum acquisition time lambda DC and the averaged acquisition time is lambda DC divided by PD. So PD is the property of detection. So in this, we are going to see a data sequence, a DSS-based search acquisition, and frequency hopping-based search acquisition. So here we have two things. Every analysis we are going to compare with the DS and FS. That's the main thing. Okay. So in this direct sequence search acquisition, which is a serial search process. It is similar to this parallel process, but quite the mixer and the correlator will be quite different. So here the timing of the PN code is set. It related to the incoming ping signal. So at the receiver, the timing being set between the transmitter and receiver, the timing has been set. The local generated PN sequence is correlated with the incoming PN signal. So there is a in the diagram you can see there is a PN sequence code generator. This clock is being generated, okay, with the received code signal, and it is been integrated and is going to compare, and it use the search control to acquire the signal, okay, or properly align the PN sequence code generator. It is a loop, okay. It is a feedback loop. It is a looping process. It goes on up to a it receives the proper PN code generator, okay. So here it uses the looping process. Okay, so and the chip lambda should be have a should be greater than 1. Okay, so lambda should be very much greater than 1, and the lambda tc should have a fixed value. So certain key points are noted here. Uh, so the output is compared to the preset threshold. So there is a threshold value. If the output is not below, if the output is below the threshold, the phase of the local generated code is incremented by a one half of the chip. Okay. So if the output output which is coming lambda DC, okay, which is output, when you compare with the threshold preset value, if it is below the value, output is below the value, so the threshold phase of the local generated code. So there is a locally generated code signal. So the phase is incremented by a fraction of one half of a chip. Okay, and the correlation is re-examined. So at the threshold, what happens when it doesn't have a less value of the threshold? It goes on looping out by fraction of one half of a chip. And when the threshold is being increased, okay, so when the threshold is somewhat have a greater value, so what happens is the PN code is assumed to have been acquired, okay, and the phase synchronization process is stopped, and the code tracking procedure will be initiated. So once the incoming output is having a very much high value than the threshold, so it will stop the looping process. It will go to the code tracking procedure. Okay, so first we see the acquisition. So once it is acquired, it goes to the tracking. So this once it is been higher the threshold is being maintained, so it goes to the tracking procedure. So this block will make sure you get a proper sequence code acquisition, okay, with respect to direct sequence spectrum, okay, by aligning the by aligning the hopped signal or the received signal at a proper level. So the maximum that is T acquisition max is given there as a formula. It's given as a maximum time acquisition is 2 NC, that is the maximum output 2 NC, which is being given as output lambda TC. Okay, so this should be a fixed value. Lambda TC should be a fixed value, and this 2 NC may vary. Okay, so in a full serial DSL, assuming it proceeds with the half shift increments, so it have a maximum time acquisition of 2 NC by lambda TC. Okay, and where at the another formula we have in the NC, okay, number of chip is very much greater than half chip. So previously we take the chip is half of it. When the half is been increment to 1 or 2 or 3, okay, you have the acquisition of one formula T twice of 2 minus PD probability of okay, delay, and 1 plus K PFA and C. So this have the same fixed value K lambda TC operative day 1 plus K 1 plus K PF. So here this time constant, they can be taken as K. K should be greater than 1. K should be very much greater than 1 as a time need to verify a direction. So one small condition is there, like in an event of false alarm, there is a chance of false alarm in a circuit. Okay, so in that case, the K lambda TC is a time penalty incurred. So what it says, like the K, the lambda, and TC should be properly in synchronized. Okay, if it is not properly synchronized, so it will produce a false alarm. For in a condition NC greater than half of the chip, and K is greater than 1. So next formula is taken as variable of acquisition. Variance of the acquisition time is given as 2 NC lambda TC the whole square, and 1 plus K PFA. K PFA is a property of false alarm. Okay, PD is a property of correct detection. So the detection should be as high as possible, and the false alarm probability of PFE should be as low as possible. But the K should be as very much greater than 1, or any condition in a variance of acquisition, we can take K as very much less than 2 NC. Okay, so these are some of the formulas which will govern or make some uh, make sure the acquisition is being done properly. Okay, and the PN generator code has been it doesn't altered, and it syncs with the transmitter. Okay, and the clock is not being delayed. So this clock as well should have a sync with this clock in the transmitter. So once you have a proper synchronization may be done with the transmitter receiver with the proper PN code generator. Okay, so here uh, at the next one, frequency hopping, uh, FH serial acquisition. I think we will see on the next session. So if you have any doubt, you can ask. So today we have seen one of the synchronization and acquisition. So next in class we'll see the tracking, and thus we'll have one quiz also, normal quiz, and we'll wind up the unit number 5. If you have any doubt, you can put in the chat. Okay, thank you, students. We'll see you on the next session.